Hi, welcome to our machine learning project for spring 2022. We are Aizhan, Allison, Daksh, Kartik, and Neha, and the focus of our project is the gender pay gap. Women earned on average 84% of what men earned in 2020. This gap has remained fairly consistent over the past 15 years, and it prevails across age groups, though wider for older women than younger women. A variety of reasons are cited for this. Societal expectations for women to stay home and provide childcare, prejudice against women in certain fields, and lower access to professional development and educational opportunities, especially in male dominated settings. However, some argue that the gap exists simply because women tend to choose professions that are less lucrative than those of their male counterparts. The aim of our project is to use machine learning methods to investigate the gender pay gap and try to predict the gender of a person given professional profile. Though the existence of a gap is widely known, many existing models ignore the critical factors needed to comprehensively understand the situation, such as citizenship status and total number of hours worked in a year. Our models aggregate these features to consider the most information when examining the pervasiveness of the gender pay gap. To do this, we use the Panel Study Income Dynamics dataset from a larger GPG, gender pay gap, dataset found on Kaggle. This dataset includes a couple of hundred features per surveyed individual, including basic demographics, age for example, household size, hourly pay, years of experience, the year the data was collected, and of course, gender. For the data pre-processing phase, we developed the following pipeline. We loaded in and explored our dataset as a pandas data frame. Next, we identified relevant features with respect to our target variable. We dropped these features from our dataset and then searched the resulting dataset for missing values. We found that our dataset was clean and complete and did not have any null values. We moved to the next step of creating and analyzing frequency distributions for values for all the features. This allowed us to address feature imbalances. For example, if a particular feature took a particular value more than 90% of the time, it is not useful as a differentiating factor. Using this as a threshold, we were able to reduce our dataset to 30 significant features. Next, we identified and removed outliers from the dataset. Finally, we performed feature selection using the chi-squared function known as the scoring function. This was used as a scoring function. This was done using sklearn's feature selection module, allowing us to select a subset of features to train the model on. We also considered dimensionality reduction via PCA for model training. However, although PCA may retain key information from the original dataset, it is a transformation applied to the original feature. This deters us from one of our original objectives to determine feature importances. Hence, we base our final training and test datasets on the result of feature selection. Since this is essentially a classification problem, finding and using the relationship between data points, people, and labels, gender, we choose supervised learning techniques, decision trees, random forests, and a neural network. We wanted to test single decision trees as baseline, then compare the results to those given by a random forest, the rationale being that the ensemble results of 100 decision trees would outperform just one. For our neural network, we went with a multi-layer perceptron classifier with one non-linear hidden layer. Input values go through this layer and are transformed by ReLU before the output layer transforms them to output values. We chose an atom solver since it tends to perform well on large datasets, and ReLU since its fast nonlinearity. A regularization term is included to prevent overfitting. In order to see if our data could be linearly separable, we also ran SVM on our dataset with a linear kernel, linear SVC. Overall, the random forest model performed better than neural network, with random forest achieving 79.2% accuracy and neural network reaching 70.7% possible reasons. The possible reasons for this include the random forest is an ensemble model and comprised of multiple decision trees. Decision trees are significantly less sophisticated than multi-layer perceptrons. However, having an ensemble of trees perhaps outperformed and overcame the fact that these models are significantly less sophisticated. Second possibility could be poor tuning of our hyperparameters. This can result in significantly worse performance, and it is possible that had we been able to successfully tune the parameter to its ideal position, we would have been able to achieve significantly higher results from our multi-layer perceptron. The bar plot that you see on the screen illustrates the most important features in determining the classification output in our random forest model. As it can be noted, the adjusted labor income and occupation can be categorized as more relevant features compared to the annual labor income and years of experience. In addition to the models mentioned above, we also experimented with a linear SVM model and got an accuracy of 73.5%. As this is a relatively high accuracy, we might have linearly separable data. If this is true, it would explain why the random forest model was more accurate than a neural network, since the highly complicated neural network was trying to find nonlinear relationships where there were none. After subjecting our dataset to the aforementioned models, we observe a distinct correlation between gender and the selected features of income, industry, years of part time work, experience, real hourly wage, and occupation. This is in line with our expectation of the trend we see in gender gap in society, specifically income and hourly wage, that were big predictors, being first and third most important features in the random forest model, respectively. Having conducted our analysis, we acknowledge that society's unfair toxicity to women in STEM industries and occupations, combined with the expectations of parental leave, could be causal factors for the significance of other important features learned by our random forest model. We further conjecture that addressing these features by representing them numerically in a way that is mathematically meaningful and by training new models with data with only a singular degree of freedom would potentially give us better results. Thank you.